Given a binary tree, you need to compute the length of the tree's diameter. The diameter is the length of the longest path between any two nodes in the tree. This path may or may not pass through the root. Okay, so now the length of the path between two nodes is represented by the number of edges between them. So we're counting edges. Count the number of edges between the longest path in a tree, between any two nodes in a tree. So in this case, the longest path is highlighted in red. The number of edges is 1, 2, 3, 4. So we return 4. Here, longest path denoted in red, count the edges 1, 2, 3. Therefore, return 3, as you can see over here. And one more example. In this case, longest path between any two nodes is the straight path, so all in red. 2 edges, count, return 2. Solution. Now, solution, the naive way is to find a distance, pick one node, find a distance to every other node in the from the selected node, and keep track of the maximum value. Repeat the process with all nodes in the tree. After this process, we will have the maximum possible distance between the two nodes, and that will be the diameter of the tree. Time complexity is quadratic, so O of n squared. Now, for the optimized path, we need to calculate the height of the left and right subtrees, return the greater one to get the diameter, to calculate the diameter, okay? Now, to get the height, we traverse the depth of the left and right subtrees. Therefore, the problem is a natural fit for DFS. You know, point of correction, I'm going to throw this sentence away. We're not just returning the greater one, the greater height between the left and right subtrees. That's really not what we're doing. And so ignore that completely. And but something else they say here is useful. The diameter is the length of the longest path between any two nodes in the tree. Now, it may or may not pass through the root. So now there are 3 cases where it passes through the root. Okay, that's case 1. As you can see here, it passes through the root. Then case 2, where it doesn't pass through the root. So like here, it doesn't pass through the root. So it's only going to pick either one, the left or right hand side of the subtree. Okay, so those are the 2 cases. So there are only 2 cases. It goes through the root or it doesn't go through the root. And now this diagram I found to be useful. We're going to use DFS, so you know recursion's coming, or like something similar to it. You can modify it to be iterative, but pretty much the same concept, fundamentally, the same way of moving through the tree. So you get the root of the tree. If it's null, right, it returns 0. There's nothing to do here. Otherwise, we get this pair that has a diameter property in it, right? And we're going to return that in here. And now this is a recursive function. The first thing we're going to look at is the root node, and it's defined here. If it's null, this is a base case. Return a pair of 0, 0. And now I want to come in here. So we pass in this root 1. So we call it, right? The root is called, right? It comes in here. It's not null. And then it comes in here to its recursive step, where it goes to the left-hand side for the first time. So it's going to happen again, but for the left-hand side. And then it's going to come again, as you can see. It's not null, but it's going to come again for the left-hand side. And then it's going to do this again, but notice that there's no left-hand side, no right-hand side. So in that case, it's going to come again, but this time, the child of 4 is going to be null, as you can see in the recursive call here. It's going to be null. And so we're going to return 0 for the left-hand side. And then we're going to pop it from the stack, and now do the right-hand side for 4. We're at the leaf node with the value of 4. We're going to do the right-hand side. It's going to give us 0, 0 as well, right? As you can see here. And then we pop that. Then we come back to 4, back to this function execution for 4. It's completed everything up until here. Then we get the height. And we're going to take the maximum height, right, between its left and right subtrees. And remember that we're returning a pair, right? So this is the definition of that. It's basically just an object with a diameter and height property. And so we can check the heights. What's taller between the left and the right, right? Whichever is taller between the left and the right, add 1 to represent that root node, okay? So in this case, left is 0, right is 0. In the case of 4, right, a subtree consisting of 4 as the root. The left height is 0, the right height is 0, and it's the only thing in there. So add 1 for it, basically. So that basically tracks the case of it passing through the root, right? And so if it didn't pass through the root, we were checking just the left-hand height, right? We would use whichever is bigger between the left and right height. If it's passing through the root, right, we're gonna factor in the root node. So and therefore pick either or and add it to it. Okay. Okay. All right. So actually, this is just calculating the height. So either way, it's gonna, whichever is taller, left or right, just add one to it to get the height of this node. So this is the height of the node. Okay. This represents height here, represents the height of the node. And so the height of the node here is going to be 1. So it's like one node high, which is itself. And so we're done with this, but then we need to calculate the diameter. So this represents the diameter of the subtree with the node we're at as its root. And so we're going to get the left-hand side diameter, which is 0, right-hand side diameter, which is 0. Okay? So this is assuming for the diameter for the left subtree, diameter for the right subtree, and the diameter assuming it's passing through the node, which would be equal to the left height plus the right height, right? So those are three. Well, it represents the two cases we mentioned, right? Either it goes through the root or it doesn't. But if it doesn't go through the root, there are also two other cases where it's okay, where we took the left-hand side or we took the right-hand side. So that's what this is going to represent here. And so we use this calculation, get whichever is larger, gives us the diameter for that particular node, because we're looking for the tallest one, right? The greatest distance. And then we return that for that node, okay? For that subtree. And so in the case of 4, the diameter is going to be L plus right is 0, right? The left hand subtree and right subtree are 0. Same with the diameter. So the diameter for 4 is 0. For leaf nodes in general, it's going to be 0. And we're going to get do the same thing now for the right hand side for 2. Remember, the recursive call stack is done for this. So it's going to come to 5. And it's going to give us 0, 0 as well. Yep. And then the height of 2 is going to be equal to the height of 2 is going to be equal to the left height of the max between these two, which is for the two of them, they're only one node tall, which is themselves. And then we're going to add that 1 plus 1. That's going to give us 2. So the height of 2 is 2. So you have to say 1, 2. Step on 2 nodes to get to 2. And the diameter is going to be the left-hand diameter, which was 0, right-hand diameter, which was 0. But the left height plus the right height is going to be 1 plus 1, which is 2. And that represents the fact that there are two edges here. And so 4, 2, 5 is the longest path. And those would be the two edges. So that's what you do. And now recursion's magic kicks in, right? And so we now unravel 2. We've stored what's there for 2. So 2 diameter, 2 height, 2 diameter. We bring it into 1. So now this part of 1 is done, right? We have this, the 2, 2 stored here. Now we're going to go to the right-hand side. And the right-hand side is going to give us, what's it going to give us? The diameter is going to be 0, but the height is going to be 1 node high. So it's going to come back here. And now we are at 1. Okay, so this is completed for our root node. We get the height, which is the maximum of the left and the right, plus 1. So the height here is 2 plus 1, it's 3, because it's not going to be this, right? It's going to be this side. So the height is going to be 3, 1, 2, 3. And then the diameter is going to be left-hand diameter, which is 2. The biggest between 2, right-hand diameter, which is 0. And then the left height plus the right height. So assuming we just took the left tree, we just returned that, and it was the tallest one, we just returned that diameter. If it was the right one and it was the tallest, we return that. If it's going through the root node, right, then we're just going to get the left and right height and return that instead. Because it's a tree, for something to be a tree, all the nodes must be connected to each other. And so we take 2 from the left, 1 from the right, add it up, going to give us 3. That's going to be our new pair. We return that, and we're done. We have 3. All right. So time complexity of DFS is O of n. Right, linear time, because you only visit everything once. Space complexity, in this case, in the worst case, right, the stack can become can grow up to O of n, where n is the number of nodes in the tree. Okay, so that's that about that. Thank you for watching. LeetCode claimed this is an easy problem, but it definitely isn't. It's a medium-ish. Some might even say hard, because if you don't know the concept, you might not be able to pull it off if you've not seen it before. So yeah, that's all there is to it. Thank you for watching, See you in the next one. Like, comment, subscribe, share. Thanks. Bye.